Hey everybody, Dr. A here, and in this video we're going to be exploring an example of a uniformly distributed moving load. Now let's go ahead and get started. In the given information, we're being told that we are given the influence line for the shear force at B on a beam here, and we're being asked to compute the maximum positive and negative shear force at B for the moving uniform load. So here we have this simply supported beam with a cantilever overhang, and we have a roller at A, a pin at C, and a free end at D. And we see these dimension lines here. We have 10 feet from A to B, another 10 feet from B to C, and then another 10 feet from C to D. We have an origin back here pointing to the right as positive, and then we have this uniformly distributed load that's moving across this beam. Now, in this particular example, we were already given the influence line, okay? So the great thing about this is we don't have to do all the front work to get the influence line like we did in the previous problem. The influence line's already given to us. So that's going to cut down a lot of the work. So the question becomes, how do we answer what's being asked of us? Compute the maximum positive and negative shear at B. Well, this problem is pretty deceptively easy once you know what you're looking at. So if you recall, whenever you have a moving uniform load, what do? We multiply the magnitude of the uniform load by the area under the influence line. Okay. Now, what you got to look at here is which areas will generate positive shear and which will generate negative shear. Okay. So think about it. If you multiply 0.2 KLF by all three of these areas together, two of these areas are negative and one is positive. And so you're going to start negating some of these areas and some of these effects, which is not correct. Okay. When you want to maximize a positive value or maximize a negative value, you only have to look at those positive or negative zones. So let's write that down. To maximize positive shear, we only consider the positive shear area. And then similar to maximize negative shear, we only consider the negative shear area, and we don't add those together, okay? So let's go ahead and tackle this. We're going to say VB max, and I'm going to put a little plus sign here for positive. That's going to, we're going to use the area, the positive area from the shear influence diagram, okay? So what I'm going to do is I'm going to say 0.2 KLF times AV positive, okay? I'm putting the V here for shear, so the positive shear area, okay? And so we're going to say 0.2 KLF times 1/2 times 10 feet times 0.5, right? Because I'm only looking at this area right here. This is 10 feet and this is 0.5. And so if I punch that through, my calculator, 0.2 times 0.5 times 10 times another 0.5. And so I get 0.5 kips. And that's part of my answer. Now I need VB max negative. So that's going to be 0.2 KLF times AV negative. And so I'm going to take that 0.2 KLF, I'm going to multiply it by these two negative areas, which happen to be the same as each other, and they happen to be numerically the same as this positive area, by the way. But we're going to say 0.2 KLF times those two areas times 1/2 times 10 feet times negative 0.5, right? Where does that negative come from? Well, that negative indicates that this is a negative area, right? So really you could tack on this negative down here because we're in like quadrant 4, okay? And so how do we crank that through? Well, we crank it through and you should get -1 kip. So that is your maximum positive shear at B, and that's going to be the maximum negative shear at B. And remember, what does this mean? What does this conceptually indicate? This indicates, we've got to zoom our brains out a little bit, zoom out a little bit. This 0.2 KLF is a uniform load. We don't necessarily care how long the uniform load is. We just care about its magnitude, and it's moving across this beam. So the question becomes, what are the maximum possible positive shear force and the maximum possible negative shear force for the moving load? Well, what will maximize the positive shear force would be if this uniform load ends up only distributed over this domain right here. That's what will maximize the positive shear force at this point B right here, okay? What will cause the absolute maximum negative shear? Well, that would be if you have like 0.2 KLF spread out over this domain and you have a gap in the load and you also have it spread out over the other negative domain right here. So for example, like this right here would be a gap loading, and you would have that uniform load only spread out over these two domains right here. That's what would cause a maximum negative shearing effect at that point B. Okay, so maybe pause the video, rewind, think about it. It is a little conceptually confusing sometimes, especially when you're first learning this. Find a good textbook, read about it, because this is some good stuff. So thanks for watching. Don't forget to hit like and subscribe, and be on the lookout for other content like this.